In this problem, we are given a current diagram right here. We have a initial voltage and we have some resistors. We are then asked to use voltage division to determine the voltage V0 across the 40 ohm resistor, then use V0 from part A to determine the current through our 40 ohm resistor, and then use this current and current division to calculate the current in the 30 ohm resistor. Then we are asked how much power is absorbed by the 50 ohm resistor. The voltage divider formula is as follows, where our V1 is V0 and our R1 is going to be 40 ohms. Also, our voltage source is going to be 60 volts because this is the voltage flowing through it. For our R1 and R2, at least for our R1, we're going to have 40. However, we don't know our R2 yet because our R2 would have to be the next resistor. There is two resistors right here, so we need to combine them. However, we cannot do that until we combine all of these, so we have to really combine everything here together. So we will get our 50 ohm resistor and our 10 ohm resistor together, and this will make a 60 ohm resistor. Then we can see that this 60 ohm resistor is in parallel with our 30 ohm resistor and our 20 ohm resistor. So we're going to use the resistors in parallel formula. We'll have a 1 divided by 20 plus a 1 divided by 30 plus a 1 divided by 60, all raised to the power of -1. And if we do this, we are going to get 10. So this 10 ohms is going to be in replace of this 20 ohms. Then we can just add our 70 ohms to it. And if we do that, we are going to get 80 ohms. So that means our R2 is 80 ohms. Now we have 60 times 40 divided by 40 plus 80. And if we do this, we can see that our V0 is equal to 20 volts. In part B, we need to use V0 from part A to determine the current through the 40 ohm resistor, and use this current and current division to calculate the current in the 30 ohm resistor. To do this, we are first going to know our current division formula. This can be found in the notes linked below, where we have our I2 equal to R1 and then our R1 plus R2 times I of S. This can be done in parallel. So what we need to do is have two parallel resistors to find this. So we're going to rewrite our circuit diagram combining all of these right resistors together. We have our 60 ohm resistor that we created from our series in parallel with our 30 ohm resistor. So we're going to have our 1 over 30 plus a 1 divided by 60, all raised to the negative first power. And this is going to be equal to 20. So I'm going to replace this 30 ohm resistor that we had with a 20 ohm resistor. Now we have to find the current flowing through the 40 ohm resistor, because that's going to be the same current going through a 20 ohm resistor, and your 20 ohm resistor is in parallel with this other 20 ohm resistor, so we can then use our current division. We have the formula that our voltage is equal to our current times resistance. We can rewrite this as voltage divided by resistance is equal to current. Plugging in our values, 40 is 20 volts, resistance is 40, we get that our I is equal to 0.5 or 1/2. So that means the current flowing through our 20 ohm resistor, since it's the same as our 40 ohm resistor because they are in series, is 0.5 amps. We can use this to define the current flowing through this part right here. Our IS is 0.5, this is the current going in our system. Our R1 is going to be the 20 ohm resistor, the resistor in parallel with it. And then down here we have our R1 plus our R2, so we're going to have 40 ohms of resistance because we have this resistor plus this resistor. This is going to give us the I2 value of 0.25 amps. A trick way to do this, because both of these resistors are the same, is to actually just half the current that's going into them. Because a current splits between two resistors, and electricity takes the path of least resistance. However, since these are both the same resistance, the current is actually just going to split evenly between these two resistors. So now we have the current going right here as 0.25. However, this is not our 30 ohm resistor. We haven't found it yet. We found the 20 ohm resistor current. And what this current is, it's really right here. This is our 0.25 amps because it splits in parallel. It'll split in parallel, and some of it will go this way and some of it will go this way to our 30 ohm resistor. So now we have to find this. We're going to use the same diagram. We're going to have our 30 ohms right here, and we're just going to combine the last part right here into its 60 ohm resistor. We know the current flowing into our 30 ohm and 60 ohm resistors system to be 0.25 amps. So we're just going to use the same formula. We're going to have our I subscript 30 ohms is equal to the R1, or this is the current opposite of it that we're looking at, which is 60 ohms, divided by R1 plus R2. This will be 30 plus 60, or 90 ohms of resistance, being multiplied by the current going into it, which is 0.25. This will give us the I subscript 30 ohms to be 0.166, and this will go on forever. My calculator rounds us at the end, so we're just going to go to 0.1667. The question asks for it in milliamps. Right now it's currently in amps, so we're going to do the conversion. 1 milli is equal to 10 to the negative cubed. That means we have our 0.1667 times 10 to the cubed, which will give us the I subscript 30 ohms to be 167 milliamps of resistance. Lastly, we are going to find how much power is absorbed in our 50 ohm resistor. We have a couple different power formulas. However, since we know the current going in through here, and we also know the resistance, what we can do is use the formula where our power is equal to I squared times resistance. We know that our resistance, because the question is asking us, is 40 ohms of resistance. We know our current is going to be the current going in, which is 0.25, minus the current that's being split over the 30 ohm resistor, which we found to be 0.1667 amps. If we do this, we're going to get 0.3469. To convert this into millis, we're going to have 1 milli over 10 to the negative cubed. And this will give us that power is equal to 347 watts approximately. And that is how you do this entire problem. It was pretty long, but that was because we had to combine both of these together to actually find some of the values. So pretty interesting problem.